Life dissected through the lens of geological time, or how the history of the Earth challenges our common understanding of life and what this implies, by João Pedro Augusto de Oliveira. Statement. Despite the active discussion on life and nature, its origin and development across the billions of years it has existed for is not common knowledge. As such, it's not uncommon for us to mistake aspects of the current expression of life for fundamentals of its nature. However, much of what we believe to be staples of life and ecosystem are in fact relatively recent on Earth's history, and through most of its existence, nature would be utterly unrecognizable for us today. Through understanding how life changed over time, we can better comprehend not only why it is as we know it today, but also deepen our understanding of its nature and potentially change how we search for it elsewhere. On that sense, the objective of this project is to demonstrate visually, through the changing of life across the eras, the flaws and misconceptions on our understanding of life. Breaking the modern view of nature. When people normally think of nature, things like trees, flowers, grass, and small birds come to mind. Yet all of those concepts are relatively recent additions in the long 3.8 billion years old history of life. Even something as fundamental for our understanding of nature as trees has existed for merely 1/9 of life's existence. But if not those, what is truly ancient? If the things that compose our intuitive understanding of nature are but the most recent chapter of its existence, what was nature before such things? Perhaps, looking at the past, we can answer our question. How we see the past. The Mesozoic era is often the first thing that comes to people's minds when thinking of Earth's ancient times. The Mesozoic is the era of geological time that happened between 252 and 66 million years ago, and it is the time of the dinosaurs. How we are wrong. Yet, even the Mesozoic composes only a fraction of the history of life. In fact, most dinosaurs that you can think of, such as Tyrannosaurus rex, Spinosaurus, Velociraptor, Triceratops, Pterodactyl, and Brontosaurus, are either from the Cretaceous period or the very late Jurassic. Then, how should we see the past? If your, if, if your intuitive understanding of the present and the past is wrong, how can you solve the problem? We can use the geologic timescale. What is the geologic timescale? The geologic timescale is a system that divides Earth's history based on both on the types of living creatures who existed and the environment. The GTS is based on the fossil record and the rock record. The GTS is divided into several units of time: eons, eras, periods, epochs, ages. Eons, eras, periods, epochs, and ages. 5 units of time compose GTS. each containing the following in incremental manner. Those are eons, time, half a billion to over a billion years. There are 4 eons. Eras, last hundreds of millions of years. There are 10 eras. Periods, last tens to 100 million years. There are 22 periods. Epochs, last tens of millions of years. There are 34 epochs. Ages are the smallest units of GTS. There are between 96 and 101 ages. The 4 eons. While eras are important and periods will be mentioned, the eon will be initially the most relevant. The Aegean Eon. Earth is born from accretion and constant impacts of planetesimals. Constant bombardments ensure hellish conditions. High volcanic activity releases many substances. An atmosphere is formed and the water falls down as rain. The moon is formed at the collision with Theia. Archean. Late heavy bombardment brings water. Oceans form from the water. First evidence of life, stromatolites. First large landmass, Valbera, forms. First glaciation occurs at the poles. Proterozoic. The great oxygenation kills 90% of life. The Uranian glaciation lasts 300 million years. The first eukaryotes emerge. The boring billion allow for most cellular life. The cryogenian lasted 65 million years. Phanerozoic. The Cambrian explosions brings complex life. Pangea forms and later splits into moderate continents. A lot happens. Extinctions, new species, billions of years of extreme conditions. Dinosaurs appear in the Mesozoic. Modern times, 605 million years ago, 65 million years after the dinosaurs go extinct. Archean, the first forms of life, 4 billion years ago. Single-cell life arose in the Archean. Their life was simpler than its modern counterpart. It was prokaryotic. It had no organelles or nucleus. Anaerobic. It did not use O2 and would actually die if it received oxygen. Chemotrophic. Used chemicals for energy. Possibly used RNA instead of DNA. Anoxygenic photosynthesis. The first photosynthetic organisms didn't use oxygen or water in their processes. Instead, they used anoxygenic photosynthesis, which can be based on either sulfur or arsenic. They use purple and dark red pigments instead of green, making the waters they inhabited pink or potentially purple. The descendants of such organisms can still be found in pink lakes. Image from Lake Kobus in Russia. Cyanobacteria and oxygen. Modern photosynthesis is developed by cyanobacteria. Using CO2, H2O, and sunlight, they could create food in the form of sugar, releasing oxygen as a waste product. Their fossils, stromatolites, are the earliest that we have found. Rusted oceans. At the time, the oceans had great iron content. The presence of oxygen caused it to rust and sink. There were several cycles of the oceans rusting. The iron sank and rusted until it could no longer absorb the oxygen. And this is actually why there are many iron bands that can be found in certain terrains. The Great Oxygenation Event. After all iron sinks, it could no longer contain the oxygen. Most organisms were anaerobic. Oxygen was poison. 8 to 99.5% of life went extinct. At this point, life was mostly single-cell, but it would actually be this event that would allow for more complex life. Since the presence of oxygen was very dangerous because it was so reactive, would allow for more energy to be gathered by organisms. This will be greatly beneficial and will be one of the reasons that multicellular life like us is possible. If not for that first extinction and those cyanobacteria, we wouldn't have life as we have it today. Uranian glaciation. Photosynthesis, cyanobacteria. O2 synthesized reacts with methane, producing H2O and CO2. CO2 is less potent than methane as a greenhouse gas. CO2 and H2O are used in the process, further reducing the greenhouse effect. Icehouse effect. The entire Earth freezes. First iceable Earth. 3 successive ice ages occur. Uranium led the Siberian and Triassic periods of the Paleoproterozoic era. The amounts of CO2 in the atmosphere increased. The increase was likely caused by volcanoes. There is evidence of a potential asteroid impact that facilitated the end of the uranium. So what basically happened here is that cyanobacteria were constantly breaking down the CO2 and transforming it in oxygen. It meant that the atmosphere was actively losing greenhouse gases and being replaced by oxygen. This meant that heat could no longer be trapped, which led to an icehouse effect, which is the opposite of a greenhouse effect. Which basically means that science end up losing all those gases and oxygen end up reacting with even other gases. It end up happening that many of the greenhouse gases end up being lost, even beyond the CO2, because oxygen is highly reactive, which is one of the reasons many organisms die. And because of that, you occurred the greatest glaciation of all time, one that lasted 300 million years, even if it was divided between many smaller ones. Eukaryotes. Eukaryotes are cells with complex structures such as nucleus and organelles. Endosymbiosis is part of the current accepted theory of their emergency. It proposes that single-cellular organisms incorporated others of different functions. The cells became so connected that the swallowed ones started acting like internal components. While this actually sounds absurd, it has actually been observed with things beyond our own. The mitochondria, for example, the ones in your body and all that, are that kind of thing. They are under endosymbiosis. They originally were not part of our actual cells. They have their own DNA and act independently. And we actually observe this happening in a few other types of bacteria and single-cell organisms coming together. It separates from what happened with plants and us. Because the plants are characterized by the cyanobacteria, actually. The cyanobacteria that made all that happen, froze the entire world, they are under endosymbiosis, or less relative of them is under that. So technically, the only time photosynthesis was developed was with them, and plants are just like merged. The same way we have our mitochondria that basically do the opposite and basically powers up. There's a reason it's called the powerhouse of the cell. So this is actually a very important phenomenon that allow for life as it is today, and will be a big step in allowing organisms of greater complexity to appear, since they were now able to use much more energy. The boring billion and the multicellular life. For a billion years, the climate will remain stable. This stability allowed for the first multicellular life. So the boring billion, despite the name, was actually very important. As I just mentioned, the stability allowed for the first multicellular life that could appear. The reason for that is because before that the climate was just chaos. It was changing all the time, events after events, the earth freezing, and then meteorites and volcanoes and all the bad stuff. But for those billion years between 1.8 and 0.8 billion years ago, was a period that allowed for life to properly develop, because there was no climate actually changing. It was a period of stability that allowed it to build itself up and actually gain a proper form in a way. The Cryogenian, between 720 and 635 million years ago. A second oxygen spike leads to the Cryogenian period. The Cryogenian is basically just a repeat of what happened prior. The cyanobacteria just really need one condition to occur, which is rising warmth and CO2. The first life forms. After the Cryogenian, the Ediacaran period begins. It's marked by the spreading of multicellular life. Sponges. There is evidence that sponges are as old as 890 million years, older than the Ediacaran, although they are likely younger than that. Sponges are potential candidates for the first living beings on the animal branch of the tree of life. But sponges were not the only multicellular Proterozoic organisms. Ediacaran life. Claudina Hartmanni. Late Ediacaran demonstrates a mineralized skeleton shell-like structure that could have developed to resist predators. Ernietta plateauensis, late Ediacaran, is the only one of its genus, live partially buried in sediments, likely passive in feeding. Euandromedra octobrachiata, early Ediacaran, a poorly understood organism that cannot be properly classified. Parvancorina minkami, late Ediacaran, bilaterally symmetrical organism. Despite similarities, it's unlikely to be an anthropod. Georgia wagoneri. Despite appearance, it isn't truly symmetrical, a possible transitional fossil between Dickinsonia and Springinia. Dickinsonia costata, late Ediacaran, probably an animal, bilaterally symmetrical organism. Tribachidion Eraldiscon, tri-radically symmetrical organism. It is unknown how it moved. Spirigina floundersi, late Ediacaran, potentially predatory. Carnia amazoni, the first Precambrian fossil to be identified as a Ediacaran, despite the appearance of it's closer to being an animal than a plant. The Carnia was actually very important. As mentioned here, it is the first identified was Ediacaran, because before it was only thought that life began in the Cambrian. So this is a very big deal. Canberella quadrata has a non-mineralized soft shell. It's hard to properly classify it. Cyclomedusa David, originally thought to be a jellyfish, but recent discoveries cast doubt on its classification. Potentially, it was a bottom-dwelling organism. Gypania spiralis, a tube-like organism, potentially worm-like. Otavia and Chica, the oldest animal fossil, sponge-like. It is the one that we refer to when we talk about the oldest animal being a sponge. Pteryginian simplex, unclear if it performed photosynthesis, likely an animal. Life in the Jacaran, overview. The Jacaran solidified the transition from unicellularity to multicellularity. It was marked by the development of soft body organisms. Nervous systems and skeletons were yet to be developed. So the Ejacaran was, as far as we are aware, their earliest point there was multicellularity. Originally it was thought that multicellular life started in the Cambrian, but that was changed because of the Charnia. So the Ejacaran, we can see there are also many animals that look very similar to plants. But that's because at the time there was a much more simple lifestyle of things basically just waiting for food to go to them. Predation, as we know now, has yet to begin to be a thing. So everything's just acting passively. The Cambrian explosion. While life grew in both complexity and numbers in the Ejacaran, it would only truly shine during the Cambrian explosion, a period of such increased biodiversity that it kick-started the Phanerozoic Eon. The Cambrian explosion is arguably the biggest deal there is. It is the point in which life went from very simple to very complex, far from what we have today, but it is still really complicated in that sense. The point where things started taking many characteristics, and groups that you know today started appearing. What did it bring? Many major groups of life. Complex structures such as nerves and bones. Primitive spines and exoskeletons. Carnivory. Predator and prey dynamics. Simple eyes. Flexible limbs and segmentation. Why did it change? In the Ejacaran, life was mostly soft-bodied, composed of producers and filter feeders. The Cambrian changed that. The introduction of predators led to life to a more proactive direction. Life shifted from soft to hard-bodied, as both defenses and weapons became necessary. Complex structures such as eyes developed, for both hunting and fleeing. Why did it happen? The cause of the Cambrian explosion is unknown. However, there are potential causes, such as an oxygen spike pushing life past evolutionary thresholds, increased calcium concentration facilitating the rise of hard bodies, a nice age forcing life to adapt hard parts and life to survive. Well, this is actually not really separated between reasons, because all of those things are things that we know empirically that happen. There was an oxygen spike, there was increased calcium concentration in the ocean, and an ice age happened. But all of those things are things that likely push life to develop the hard parts and ice and all of that. But here's more proposing what in specific led to it. but it is more likely that it was a combination of all of those trees and even more factors. Phylum Chordata. The phylum Chordata, which all vertebrates belong to, appeared during the Cambrian, while proper spines were not developed until much later. Cambrian chordates were developed a flexible dorsal cord, used for swimming, that functioned as the center of their nervous systems. Examples of Cambrian chordata are Picaia gracilens, Ionanozan lividum, Zongi gianikitis, Hycoikitis. So they are very relevant. The Hycoikitis is the potential first fish. You can really see written there. That bad boy here is a very good candidate for the first fish. There are also the earliest known vertebrates, which is the name here. So at that point is basically your most ancestral ancestor ever. Of course, they're even earlier, like cell ancestors and stuff. But the point that things with the spines, which is basically at some level, start to appear is about here. They look more like worms, but they are going to later develop to fishes, which are going to be the first to actually have the spines. The trilobite bone. Trilobites. An extinct group of arthropods were split into three segments, being arguably the most successful species during the Cambrian. It is speculated that trilobites could predate the Cambrian. Trilobites lasted for 300 million years. Over 25,000 species of trilobites have been identified. Radiodonts. Radiodonts are the earlier superpredators, sharing similarities with shrimp and lobsters. Some of its members, like the Ophabina and the Anomalocaris, are some of the most well-known creatures of the Cambrian. Not all radiodonts were predators. Some were filter feeders or sediment sifters. Ophabinia, counterbarrial predator. The Ophabina's trunk, like claw, was likely meant to catch small burrowing animals that had become common at the time. Ophabina was the only known ophabinids until 2022, when a previously thought to be Ophabina fossil was reinterpreted as another genus, the Utaurora. Ophabina was between 4 and 7 centimeters in length. Hallucigenia, the bizarre. The Hallucigenia had baffled scientists for years, the position of his head and legs being misunderstood for more than a decade. Its spikes were likely meant to protect it from the radiodonts predators. Its length was of 30 millimeters. Since jaws had not yet evolved, it likely ate by closing and opening its circular mouth. Anomalocaris, the apex. The Radiodonts Anomalocaris can be considered to be the apex predator of this time. It was extremely large by Cambrian standards, reaching 38 centimeters. Anomalocaris' frontal limbs could serve a variety of purposes, such as grabbing prey and bringing it to its mouth. Anomalocaris likely swung by undulating its lips. Its compound eyes were some of the most well-developed of its time. The Cambrian period ends. 495 million years ago, the Cambrian period would end with the Cambrian-Ordovician extinction event. It was caused by a combination of falling oceanic oxygen levels, toxic sulfur compounds, and a series of smaller extinction events. It's speculated that it was led to by volcanic activity. The Ordovician period begins. The Ordovician's beginning. The Cambrian-Ordovician extinction events caused many of the niches, rows of organisms that were taking the Cambrian to become open, allowing for other beings to take those niches through adaptive radiation. The Great Ordovician bioreversification events, GOB, acted like a second Cambrian explosion, causing a great amount of diversification within the groups established in the Cambrian. The first coral reefs started appearing. Gastropods, bivalves, rhinoids, coelites, cephalopods, trilobites, and rhizoans diversify or appear. The retired predators. The radiodonts were forced out of their role as Earth's first superpredators as the number of large prey fell. However, they would find grand success as filter feeders thanks to their increase in plankton diversity brought by the Ordovician. AOG urocastis is an example of a giant radiodont filter feeder, reaching upwards of 2 meters in length. So effectively, the radiodonts right here started taking a role more akin to whales. Similar to them, they use a way to basically catch all the plankton and consume them. It's a strategy that is highly effective and allows beings to grow extremely large, hence them being one of the largest animals of time ever. Terrestrial plants. Plants were the first complex organisms to colonize the land, but those plants were nothing like the ones we are familiar with today. They did not have any vascular structures such as stems, being similar to moths and liverworts. Such plants are known as lycophytes. Lycophytes became truly successful when they developed the ability to produce spores, which allow for effective reproduction on land. Research suggests those earlier plants may have been supported by fungi. So, the ability to produce spores here is very important for a multitude of reasons, because their old methods were completely ineffective, mostly because in the waters it was much easier to pass down genes, since the currents will take whatever you wanted in anywhere else. So, because they were able to develop those spores and gain a certain motivation to even go taller, because to spread the spores better because of their size, this is what allowed them to become widespread here. Perhaps not so deadly squids. The usage of a straight cone-shaped shell, orthocone, became a popular body plan for nautilus cephalopods in the Ordovician. For some time, all of the cephalopods with this body plan were classified under the catch-all terms Orthoceras. Now we know they were of different groups. A popular Orthoceras is the Endoceras, reaching upwards of 5.73 meters. Because of their size, researchers popularly think them to be apex predators, akin to modern cephalopods of similar size. Modern analysis could indicate they were plankton-eating filtrophilids that traveled horizontally. That did not mean there were no predatory Orthoceras. Some were likely very deadly. Okay, so the orthocone thing, or the classification of them as the same Orthoceras, came from the fact that you cannot really preserve squids. Okay, they're not really squids, but the thing is, they were still mostly muscle and mostly flesh, which doesn't really preserve well. So what researchers found were their cones. Their cone-shaped shells. Because of that, there ended up being the idea that they were all in one single group, when in fact they were basically a multitude of beings, with something happening quite similar with like crabs, which various beings in related families are taking a similar style. Deadly sea scorpions. Eurypterids, while not true scorpions, demonstrated a similar body plan. The earliest known Eurypterids, Pentecopterus, lived about 467 million years ago. It reached about 2 meters in size and was a bottom feeder, a predator that hunted in the seabed. Armored fish. To deal with the dangerous predators, the fish-like organisms of the time developed a characteristic not often associated with their descendants: armor. Arandespis. He had no jaws or fins, swimming with its tail like a tadpole. It lived in shallow waters, being between 12 and 14 centimeters in length. Its most notable trait is the presence of scutes and bones, acting as armor for its body. Succubombaspis. He also lacked jaws and fins, swimming in a similar manner. Its head was covered by armor, being flat and wide. Its length reached 27 centimeters. It demonstrates signs of a lateral line, an important sensory organ for fishes. The Ordovician Silurian mass extinction. Icy house glaciation destroys the habitat of shallow water and warm-adapted organisms. Greenhouse effect heats up the globe and destroys the life that survived the glaciation. 85% of the species on Earth go extinct. As the supercontinent Gondwana moved towards the South Pole, it became covered by glaciers. The cooling caused the lower sea levels, destroying shallow water ecosystem. The species that survive, generalists and cold-adapted life, would then suffer as the climate started warming at a rapid rate. As the ocean heated, its oxygen level fell, suffocating most of the remaining species. The extinction was likely caused by the effects of terrestrial plants on rocks. They liberated high amounts of phosphorus, causing massive booms in cyanobacteria and algae populations. After they died, they were broken down in highly oxygen-intensive processes. Silurian period. The Silurian period was marked by the heating of the globe. This caused sea levels to rise, creating many shallow sea habitats and inland ponds. The newfound presence of shallow sea and pond inhabitants, the plants that now live in land, and the fierce competition in the ocean led to the first few organisms to live on land. Vascular plants. For the first time, plants with vascular tissues had appeared. Those plants lived close to freshwater ponds and other sources of water. With vascular systems, they could grow taller and better absorb the energy from the sun. Those plants did not grow taller than a few dozen centimeters. Cooksonia. It is the oldest known vascular plant. It was very common and reached 30 centimeters in height. Physoliphyton. It is more complex than other plants of similar age, branching much more than others of the time. Baragiwanatatia. One of the first plants to show true leaves. It is related to clover-mosses. Fungi, the true lords of the land. Plants were not the true rulers of the land. Prototaxites, giant fungi resembling the tree trunks, compose what would be called the first forests. New research suggests they could grow both vertically and horizontally. Prototaxites could grow up to 8 meters tall, being by far the largest living being on land. Their size was likely for the spreading of spores and was supported by a huge mycelial network. It is possible, like earlier fungi, Prototaxites facilitated the creation of soil viable for plants by releasing digestive enzymes that weaken the ground. The rise of the fish. Chordates changed and diversified, gaining many of the characteristics we would have come to associate with fish today, such as jaws, skeletons, and fins. The development of the first jaws is arguably the most important, allowing them to bite and consume food in an active manner. It also opened the way to the first fish predators such as megamaxtas. So the reason that the development of jaws is so important is because, as it says here, it allowed them to actively consume food. And while that does not seem impressive or important, before that they didn't really have any offensive option. Since they now could hunt in an effective manner and could gain much greater access to food, that opened the way to fish that could grow way larger. And as such, the first fish predators started appearing. The paths of fish. The presence of jaws allow fish to diversify and branch into many different forms. Gnatostomata, fish. Placoderms, plankton fish. Acanthogens, spiny sharks. Osteichites, bony fish. Chondrichthyes, cartilaginous fish. Actinopterygians, ray finfish. Sarcopterygi, low finfish. So here we see the consequences of the jaws developing by the high amounts of biodiversity that started appearing when it came to fishes. From the eventually come to become sharks to things I cannot even imagine, like armorfish. There were many different branches that started appearing because now they were an active player. The jaws allowed them to basically take any and all roles that involve eating, allow fishes to truly become predators. And because even the smallest fish today is basically predators, this was a big change, which allowed for many developments as new niches became available. sea scorpions, traditional and new. Despite the diversification and development of fish, the true rulers of the sea would be the eurypterids. This is because after the extinction, most of their competition was gone, allowing some of the eurypterids to expand beyond bottom feeding and furthering the role of a predator in the form of Eurypterina. Although another much less common suborder, the Steinolurina, kept a role similar to their ancestors, scavenging in the seabed. Yet they brought their own unique touch. Steinolurina, Myceteropoidea, was a swift feeder. They were the last of the Eurypterids to go extinct. Styloneuroidea was a scavenger. Between the Steinolurina families, it is the least well known. Eurypterina. Eurypterus was so successful that it composes 95% of our Eurypterid fossils today. Pterigatus was the apex predator of the Silurian, having claws reaching up to 1.75 meters. Arachnids and millipedes, the pioneers of the New World. Outside the chaotic water was a sanctuary without predators, a place filled with food and no competition. This led a few arthropods like arachnids and millipedes, to begin to adapt to the land. This process took millions of years, since they had to develop the ability to breathe air, handle gravity, deal with the different pressure, keep the water within their bodies. But after they developed such traits, they thrived within the new frontier. Devonian periods. The Devonian period didn't begin with an extinction, yet a lot changed from the Silurian. For example, a general trend within the Devonian is an increase in size in most organisms. The creatures in the ocean and the plants on land being the greatest example. The greatest changes occur on land, with the first terrestrial vertebrates and the rise of trees. But the oceans would also meet many innovations in the form of sharks and large fish. Stromatolites and corals. Changes in climate caused the death of most coral reefs. In the earlier Devonian, yet reefs would still exist within stromatolites, formed by cyanobacteria as a basis. Many organisms will thrive within the ecosystems those reefs provided. They will not last more than a few million years, however, as the temperature cooled out enough to allow corals to rise again. They triumphed over the slow-formed stromatolites. So this is actually very interesting, because what occurs here is that while the corals are very, very successful in a few specific climates, they are extremely highly specialized, which is see today because many coral reefs are just dying. This is because they are very vulnerable to changes in climate. However, the stromatolites, on the other hand, are much tougher, and exist even today, being arguably like one of the earliest formations possible, since they were the first fossils ever found. But the thing is that they are way too slow to form. So because of that, most of those have disappeared today. But there are actually still places we can find some of them. The sea of sharks and fish. The first cladodonts, sharks, branched from the cartilaginous fish and take on a predator lifestyle. Yet the first sharks would be second to the fishes that truly dominated the Devonian, cladoderms. At the time, the cladoderms started growing in size to the point of being much larger than the average person. They took both filter feeder and predator roles. Dankylosteus is the best example of placoderm predator. It had a beak-like jaw and could apply over 80,000 psi of force with its bite. It used to be believed that it reached over 9 meters, but modern techniques since suggest it was closer to 3. The presence of fish, the first sharks, and such powerful fish predators led to the fall of the Riptorina, the sea scorpions. The usurpers of the lands. The extinction of the prototaxites was one of the main factors that allowed for the first trees to develop, being likely caused by its failure to endure being consumed by insects. The evolution of food was revolutionary development that allowed for the first trees, such as Watieza and Darchaeopteris. Fruits had yet to evolve, and while seed-bearing trees, gymnosperms, were developed during the Devonian, most of the first trees reproduced through spores. So here we can see the plants were very different from today. They just developed wood and still didn't even use fuse widespreadly. If actually flowering trees will come much later, even after the dinosaurs. So even if they do look similar, we can see some of them here, that they look pretty similar for the ones today, they work extremely different. Those who walked on 4 legs. The first tetrapods evolved from the low-fin fish. This was likely caused by the presence of such dangerous predators in the sea, pressuring vertebrates into going onto land. Tiktaalik is popularly referred to as the true link between land animals and fish. It had several fingers and at that point still needed water to lay its eggs. Devonian mass extinction. The Devonian mass extinction ended with a series of several extinctions that culminated in a mass extinction event. The extinction took place during a period of between 500,000 and 25 million years. It is believed that during that period, as many as 7 distinct extinction events occurred. While more than 70% of species went extinct, oceanic environments suffered the most, losing upwards of 95% of its vertebrate biodiversity. Carboniferous periods. A giant power vacuum opened in the ocean, allowing for many species to diversify and take on new niches. The land underwent something similar, but for different reasons. Life started to cut ties with water. Tetrapods started diversifying further, adapted to land. Trees became much more common, allowing life to go beyond bodies of water for the first time. Oxygen levels reached upwards of 35%, much greater than today's 21%, allowing for insects to grow larger. The World Wide Woods. The humid climate of the Carboniferous allowed plants such as trees to be able to expand beyond the surrounding bodies of water. Without this limitation, they were able to cover most of the world, creating rainforests and swamp ecosystems. Since there were no bacteria that could liberate the carbon from the plants, all of the carbon stored became trapped in the ground. This combined with them being so widespread, meant they became the source of most of our coal. In a way, by burning coal, we are returning the climate to how it used to be before the Carboniferous. So this is actually very interesting. Here we can see how the past millions of years and how it affects the now. So a lot of this ends up having to do with geology, and that's one of the big reasons. There were many events that basically left their marks in the ground, and this was one of them. Mostly because of the trees and all of that, but other examples were the ice and basically everything here, because as the atmosphere changes, we can also see the ground changing. And also, other thing that comes with it is the fossils, the change of time. See more or less animals with those climate shifts that you can identify by how the ground changes. And through that, we can create the whole geological time scale. Titan-sized bugs. The increasing oxygen levels allow for insects to grow larger. Oxygen was not the only factor in their growth, however. The lack of predators was also important. It is important to remember that most insects were still relatively small. An example of giant insect and the largest land arthropod is the Arthroplera. Estimations say it could have reached over 2.6 meters. Insects were the first to develop flight. This ability would provide a great advantage for the bugs that could use it. Meganeura was one of the first bugs to make use of this ability, and was the largest of its kind, with over 70 centimeters in length. Although Meganeura resembles a dragonfly, it actually was a griffinfly. So what basically happened here occurred because of this square cube law. So normally bugs are limited by oxygen. Unlike us, they don't really have lungs, so they need to absorb it through openings in their skins. But the problem is that the surface area is much smaller than sides, because as you grow larger, the inside basically growing volume by like 3 times. This ends up meaning that the insects today are limited by the oxygen they have. But since there was more oxygen, the limit was raised, because now the amount of surface area needed to absorb the oxygen for them to survive meant they could expand more. First, amphibians. Some tetrapods became true amphibians, developing webs between their fingers and weight-bearing limbs. Many of those were crocodile-like rows, being ambush predators that stalked the shallow waters. An example of crocodile-like amphibian are the Eriopis, which could grow to 3 meters in length. Not all grew to such sizes, for example. The famous Diploclaulus could only achieve 1/3 of the size. Some took completely different body plans. The Cholaraderpiton, for example, used a snake-like body plan. Defections of amniotes. The first amniotes, tetrapods capable of fully living in lands, evolved from amphibians. The amniotes had 2 main abilities that separated them from the parents. Thicker skin prevented water from leaking from skin, meaning they suffer no risk of drying out if they stay out of water for too long. Amniotic membrane allow for eggs to be hatched on land by keeping water inside the shell, holding nutrients and allow the diffusion of air. The amniotes will branch into 2 forms, the sauropsids and the synapsids. Sauropsids includes reptiles and birds, had either 2 or 0 temporal fenestrous openings in the skull. Synapses includes all mammals, had 1 temporal fenestra opening in the skull. Casanera is the earliest known sauropsid and was the first animal to have claw fingers. Archaeopteryx is the earliest known synapsid and was the first animal to have pronounced canines. So this is actually a very important point, because amniotes, said here, are the tetrapods capable of full living lands, and there is a ladder, and they basically spread into all land beings right now. Mammals, besides amphibians, all first mammals we descend from them. Reptiles and birds also descend from them, but like the sauropsids, and we are the synapsids. So this is a main point here, because one of the main reasons things were bound by water is because, well, why that's basically unthinkable to us. They basically leak the water through their skin. because most organisms struggle to keep water in the body, because they are adapted to an environment where water was literally basically just air, it was all around you. And the amniotic membrane, which is eggs, allow for the eggs to keep the water. So now you had the water inside their eggs, because that was needed for the process of babies and all of that. And by keeping the eggs outside of the water, they were able to do things that become completely separate from it, which allow for the exploration outside of the water, which basically all water beings were connected to and had not much of the escape. The Carboniferous rainforest collapse. Planned selective removal of CO2 led to a cool and dry climate. Amphibians, bugs, and the trees suffer from the new climate. Fungi forms live in the climate even drier. The Carboniferous rainforest collapse. The rainforest collapse, a minor extinction event that ended the Carboniferous, was caused by the plant's unregulated growth and absorption of CO2. As no form of balancing their growth or releasing the CO2 back to the atmosphere existed, the lack of greenhouse gases caused the world to cool and led to the formation of ice caps. This made the world much drier, making it harder for the trees to survive. This was worsened as Pangaea was formed, its size making it impossible for rain cloud to reach its center. Without the habitats the trees provided and a very different climate, the rest of life suffered. Yet the amniotes, having characterized of water, would undergo much smaller losses. Permian period. The formation of Pangaea and the coming of an ice age led to the Permian having a unique climate. In the coast, the forests reassembled the ones in the Carboniferous, but most of the land was a giant arid and dry desert, and intuitively, the ice age made it worse, as there was less liquid water to go around. This combination of phenomena meant the world was split in three extreme climates, would be one of the main driving forces on the beginning of this period. Gymnosperms, the survivors. Gymnosperms, plants with seeds, had existed since the Devonian, but only now they would become the norm. During the Permian, trees would come to resemble their modern counterparts, although fruit-bearing and flower trees will not appear for at least 100 million years from now in the Cretaceous. Seeds were much more resistant to climate stressors, meaning the extreme environment led to them becoming dominant. It was Glossopteris. It was very successful and its distribution was on the first evidence for continental drift. Peltas spermalis. It is possible some use insects for pollination. Walkia, a primitive conifer tree. Bug-sized bugs. With the plants forced to the coast, insects no longer had the oxygen to maintain their large eyes, and predator rose, meaning the remaining insects were forced to remain on a smaller scale. Despite this, it was at that time some of the most accessible branches of bugs appear, such as the first flies and the first beetles. Thermoregulation, the synapsid's crown. It is not surprising that the ability of creatures to regulate their own temperature would vastly improve during the extreme climates of the Permian. Synapsids would show themselves to be by far the best at it, using sails full of veins so that blood could exchange heat with the environment. The most popular example is the Dimetrodon. This ability allows synapses to be very successful in the earlier Permian, as they colonized most of the world while other groups failed to handle the climate outside of the coast. This caused them to diversify on a colossal scale. The rule of the mammal lizards. The synapses would branch into many different forms, thanks to the availability of niches in the desert. This meant that adaptive radiation was in full effect, which led to synapses taking many different roles. Despite their resemblance to dinosaurs, they were actually the ancestors to mammals. The true dinosaurs will descend from the sauropsids. Dimetrodon, Edaphosaurus, Tetraceratops, Cotyloorhynchus. Mid-Permian extinction. As the Ice Age ended, it became hotter. Arid regions started even drier, and the coastal regions being flooded. This was caused by the large mountain ranges that had been formed. They were trapping the water within the coast, creating floods. 25% of plant biodiversity died, and many other species suffer from the climate and the lack of plants. The rhapsids and cynodonts. Despite the extinction and the millions of years of extreme conditions following, by the late Permian life was once again thriving, and synapsids were still ruling the form of the rhapsids and cynodonts. It was at this time that more mammal-like characteristics developed, with a shift in skeletal structure living directly under the body, unlike amphibians and reptiles, which had then closer to the sides. Cynodonts are the group from which all modern mammals will descend from. Sauropsids also developed. The sauropsids were not idle while the synapsids grew. In fact, the first vertebrate to ever take to the air was a sauropsid, the Coelurosaurus. Although it was limited to gliding between trees, the other vertebrates will later take similar strategies, and from there develop power flight. A few lineages, rather than taking the first step for flight, returned back to the waters. The Mesosaurus took a unique body plan, with no other no aquatic organism, living or dead, taking a similar strategy. The Great Lion. The deadliest extinction events, ending around 90% life on Earth. It reduced ocean biodiversity by over 96%. It lasted around a million years. Its true cause is unknown. Wrap up. While there is much more to life's history in the Mesozoic and Cenozoic eras of the Phanerozoic Aeon, it is after this point that it becomes truly recognizable to us, with the introduction of the dinosaurs. As such, this presentation will not cover the time after the Paleozoic era. Yet, within what we covered, we can find many trends when it comes to the development and growth of life. For example, every time an extinction event happens, be it because of a changing climate, natural disasters, photosynthetic organisms, or a cosmic event, life tends to change and diversify. Often, those events cause the groups at the top to go extinct or suffer losses of biodiversity, leading to other groups more fit for the new climate to diversify into their own roles and sometimes entirely new niches. The greatest example of such phenomena is actually the dinosaurs. When the dinosaurs went extinct, the mammals became the more popular race, effectively diversifying and taking on the roles that the dinosaurs could no longer fulfill. Since the dinosaurs were too big and too specialized to the old climate, when the conditions that followed the meteorite, which was exactly what killed most of them, went on and on, they weren't really able to handle them. Since the ones that were really big could not handle the food, and the others just didn't really have the same opportunities as before. This allowed the small, more versatile and less specialized mammals to then start taking specializations and entirely new niches. It's very interesting because, in a way, the mammals are reclaiming what they once had. As before that, as we discussed, there were some sort of proto-mammals who were the ones at the top until they themselves suffered through an extinction event, which will later lead to the dinosaurs. So this permutated the majority of history of Earth. That is a very big defining characteristic. In almost all points and eras are end up being defined by such events, as those are the greatest drivers of change and end up being what defines the boundaries between each geologic era. Conclusion. While we often search for alien worlds through space, time reveals to us just how alien our own world is. Once, Earth was hell, then a snowball, then a jungle. Once there were no predators, no trees, no birds, no mammals, or reptiles. Therefore, understanding the rich history of life on this planet and the relation between the world and its residents allows us to gain a unique perspective, and is essential when we ourselves are actively influencing it. And that's why I believe it's important to clean the misconceptions of how we think of the past's evolution and the process of which life began and then later developed. Because now, when you ask about someone, what you likely come to their heads is, oh, there was like the primordial soup, first bacteria, organisms super simplistically emerge, and then they become like fish, and then those fish then grew legs and local land and diversify on literally everything ever. And then just the dinosaurs, meteorite, and dust. And just everything I show here, I will demonstrate that this is a very, very flawed understanding. We never even got to the dinosaurs, and the whole part was just not there. There was a whole history, a whole time and process in which things developed, in which the things we are used today, like the trees and everything, started becoming. We see points in which the roles of certain aspects of life were reversed, in which fungus took the roles of trees, in which the roles of animals and species shifted as events after events occurred, as the climate changed, as the creatures influencing the climate and the climate influencing the creatures. I think it's really important that this understanding of the development of life is taught, that it becomes common knowledge, because it affects how many people view the world and understanding it, how life shaped it and it was shaped by life. I think that's a very important thing, understanding how exactly this process occurred. I think it's primal, especially in this modern time in which the environment and nature and the world become more and more important as we understand how interconnected the things actually are. And I believe this should be something that is known, that is understood, that we should truly comprehend, and that when you ask someone, they should have the idea that, oh no, there was a whole period, there was like this allure, and there was everything there and everything that happened, that there were those processes, those active extinctions, and how they shaped the world. And I think that's something that's worth knowing, that's something that's worth spreading about, talking about, that people should know about those things. References: